This video is a brief overview of the paper Learning Deep Classifiers Consistent with Fine-Grained Novelty Detection. This work is by Jiacheng Chen and Nuno Vasconcelos at the University of California, San Diego. For various reasons, the ability to perform novelty detection is of vital importance for deep Bayesian classifiers to be deployed in the real world. In this work, we focus on a special case of novelty detection, where seen and unseen classes can be from a common category. This case is especially challenging and referred to as fine-grained novelty detection. The essence of a novelty detection algorithm is to design a novelty score that measures whether an example belongs to a training class. Two popular choices are probabilistic score and the distance-based score. The former estimates the generative probability or the class-conditional probability of an example. The latter aims to find a distance matrix between examples and seen classes in the feature space. In this work, we show that these two philosophies can be unified in the framework of CNN learning, but both the probability distribution and the associated statistical distance are not identifiable from the trained network. For this reason, the regular CNN classifiers are not consistent with novelty detection. To show this, let's start with some basic concepts. A CNN classifier estimates the class posterior probability of examples by a nonlinear embedding and a softmax regression. CNNs are typically trained by minimizing the cross-entropy loss. Using the base rule and the class posterior probability, it's easy to derive that the class conditional distribution in the CNN feature space is in the form of an exponential family distribution whose sufficient statistics and canonical parameters are given by the CNN embedding and classification weights, respectively. However, simply given the sufficient statistics and canonical parameters, we cannot identify an exponential family distribution. For every exponential family distribution, there is a unique Brugmann divergence, and its probability density can be expressed with this Brugmann divergence. Hence, for exponential family distributions, using Brugmann divergence for novelty detection are equivalent to using the class conditional probability. However, for the same reason, this Brugmann divergence is unidentifiable either. Our objective in this work is to make the class conditionals identifiable by adding training regularization that enforces particular exponential family distributions. Specifically, we chose the Gaussian distribution for the simplicity. In this case, the corresponding Brugmann divergence becomes the Mahalanobis distance, which is simple to implement. This lemma provides us with a condition for the class conditionals to be Gaussians. Noting that this condition is on the classification weight and the class conditional means and covariance, we propose to parameterize these means and covariance by learnable parameters. Then, a regularization loss is used to encourage the satisfaction of this condition. This loss consists of two parts. First, the parameterized class conditional means and covariance should fit the data distribution in the feature space. This can be done by a negative log likelihood minimization. Second, the embedding should adapt such that its class conditional means become equivalent to the parameterized means. This can be achieved by minimizing the Mahalanobis distance between the embedding of training examples and the parameterized means. Combining these two parts, we have the class conditional Gaussianity loss. Under this regularization, the CNN classifier has class conditional distributions that can be identified as Gaussians. The Gaussian density and the associated Mahalanobis distance can be used equivalently for computing novelty scores. For this reason, the proposed method is referred to as novelty detection consistent classifier. In this work, the proposed method has been evaluated with two network architectures on 4 public datasets, including 3 fine-grained visual categorization datasets. For our method, we experimented with 2 different parameterization strategies. Empirical evaluations and comparisons demonstrated that our method achieved significant improvement over several state-of-the-art novelty detection approaches. It is also shown that while our proposed regularization significantly improved the novelty detection performance of the CNN classifiers, it has little effect on the classifier's accuracy for the training classes. Please refer to our paper for more discussion and implementation details. This is the end of the video. Thanks for watching.